Kumar Kamalasadan from University of North Carolina at Charlotte. Dr. Sukumar is a director of the Power, Energy, and Intelligent System Lab within the Energy Production and Infrastructure Center at North Carolina University. He received his PhD degrees in electrical engineering from University of Toledo in Ohio in 2004. His research interests include inverter-based resources modeling and integration, data-driven approaches to power grid modernization, smart grid, microgrid, power system operation and optimization, and power system dynamics, stability, and control. Dr. Sukumar project has been funded by so many different agencies, such as U.S. Department of Energy, National Science Foundation, including the Carrier Award, and different companies such as Siemens Energy, Duke Energy Corporation, Schweitzer Engineering Lab, and several other companies. He has published more than 250 research journals and conference papers, and has delivered more than 100 talks in different forms of tutorials, keynotes, panels, and webinars. So as you see that Dr. Sukumar has a huge background on the different aspects of the power grid, and I'm sure today we will learn a lot from him. So with that, Sukumar, back to you. So floor is yours.
Okay. Thank you. Thanks, Saeed. Thank you for inviting me for this talk. It's always good to see familiar faces, friends, and socialize. Much of my talk, I will focus on specific one topic. So the title of my talk is Management and Control of Electric Grid with Inverter-Based Resources. I will be focusing on one aspect of management and control of IBRs in the distribution electric grid. That will be the talk for today. I cannot see your video or faces, so most likely I'll be going through my talk as we discussed earlier. Any questions and comments? If you have it in between, if you think you may forget towards the end of the talk, you can probably type it in the chat window or some right side, and we can pick up those questions later at the end of the talk.
Yeah, sure. That sounds like a good plan. Yeah, sure.
Yeah, the phone, Teams didn't work, so most of the time I'll be talking to a computer. So the title is Management and Control of Electric Grid with Inverter-Based Resources. Slides. A brief bio sketch about me. Like Saeed mentioned, my main interest is on started with power system stability and control at the power grid during my graduate program. And then from then on, we started working on management and control aspects, then got interested in renewable energy integration to the electric grid. Then worked on bulk grid level renewable integration for quite some time, especially with the wind and solar wind farms, basically, for 5 to 10 years, and moved on to the distribution electric grid. I recently started looking into things like a DER management, support of critical infrastructure, active distribution system management and control, data-driven management and control of power system. So this is like a presentation outline. I will be talking specific items from this list, bringing on introductions and overview of electric grid infrastructure, focusing on, like I said, distribution electric grid, integration of renewables as IBRs, inverter-based resources, challenges and opportunities, the need and modified management and control of electric grid, especially on the distribution network. Then we'll focus on recent work that we did with the help from Department of Energy funding on future distribution management system generic framework, basically integrating an architecture with the DMS, so-called distribution management system. We'll talk briefly about the main aspects of that architecture. That will be the main thrust of the talk. I will also talk briefly on a couple of control architecture for inverters, which can help operate inverters or IBRs in grid connected mode and also on islanded mode, so-called, or not grid connected mode. So these are the couple of items that I thought I will introduce during this talk. So we all do know that bulk power grid and the distribution electric grid complexity has been increasing with renewable energy integration into those, both on the bulk grid level and the distribution grid level. The two other important items for the electric distribution grid is obviously, other than variability, uncertainty, allocation of renewable energy resources, is also to do with the size and the large number of renewables distributed across on the electric distribution grid. And then we name that as a distributed energy resources. And much of those are managed by inverters. So the name inverter-based resource. So management of inverters and inverter-based resources control is becoming a key aspect on the renewable energy integration to electric grid. So just want to highlight that. That's one main aspect. Then demand supply balance, because of the variability and uncertainty of renewables, introduce us to have energy storage as a requirement. And energy storage also can come in different forms, as you may all know, on the visible energy storage, meaning in front of the grid and behind the meter energy storage requirements, and as well as the bulk grid, you will have larger bulk grid level energy storage. So this is two main thrust area that needs to have clear attention. On top of that, energy system planning and resource allocation of renewables is becoming a priority. Also, there are in the bulk grid, especially on the power quality stability improvement aspects, are also important. And then comes the optimal management and other operational guidelines for economic stability, reliability, and resilience improvement. So three highlighted areas that are extremely critical for electric grid, especially distribution electric grid, is IBR management, storage device requirement and management, and optimal management of the grid as a whole, connecting these renewable-based resources together to improve the reliability and resilience. So that being said, we are not yet there with the renewable energy integration, in which the goal is to have 100% renewables, which could be a reality, but there are several challenges associated with that. The goal is to have 100% renewable pledge that happen from different countries, at least by 2050. That's the goal. And the issues that needs attention is reliability, resilience, and energy equity of 100% renewable electric grid. So with this, additional support infrastructure for efficient and effective operation of the electric grid is a critical need. So in all these improvements, you need resources, especially the IBR support resources like energy storage, management capability of inverters, including controls, and grid level management. So these are the main three critical aspects. So what are we with respect to the distribution system as such and integration of renewables in there? So this is just a general topology of distribution network in the US. In other countries are slightly different. I was in Australia, they have 129 kVs considered to be in the electric distribution network. So there are some variations in here. So you have laterals, you have single two-phase, three-phase lines, then you have secondary distribution system, primary distribution system, substation level. This is a general topology. So we have renewables connected in there in the three-phase, single-phase, two-phase, in front of the meter, behind the meter, distributor all over on the electric distribution network. The current management infrastructure of the electric grid includes the distribution management system on the power distribution side, and then divided that into the recent management infrastructures like DERMS, Distributor Energy Resource Management System, which includes microgrid management, field optimization, and then on the other side, advanced distribution management system, including automation, outage management system, and then have other newer management methods like home energy management system, meter data management system, GIS information, and so forth. So the advances what we have so far on the distribution side is integration of these new functionalities under the bucket called ADMS, and the management of renewables under what we call it as DERMS. So what we don't have is a framework that can actually utilize the distributed energy resources in the field and manage to gather and connect that with the DMS, ADMS infrastructure. So that's basically where that gap is so far, even though the DERMS architecture will control individual assets and send, for example, set points for control or device operation of individual level. As far as the infrastructure is concerned, we have communication infrastructure on the substation, communication infrastructure going to the field devices, like switches, breakers, volt-watt devices, legacy controllers in the field, and communication infrastructure going to grid level or visible newer assets, inverter-based assets, like energy storages and the PVs, for example, large scale or utility scale, we call it. So that's where we have. And then that is connected to an enterprise bus, and where the enterprise infrastructure is there, looking at the operation bus software service infrastructure with DMS, outage management system, all sitting on that central framework. So to integrate the visible or so-called grid scale or utility scale IBRs, we have this connectivity through the communication infrastructure, but at the consumer level, we only have one gateway that goes to the internet from the smart meter in front of the meter side. So if you were to also look into what are the feasible way of managing the grid assets, including the IBRs, we should have at least in our utility areas, the talk is to have at least one or two asset that we can manage, not necessarily a lot. If you have a lot of those assets where we can control, it's good, but it increases the complexity. So that's basically the thought process here. So the controllable asset has to be few, and that could be managed by the utility, but those assets will have a flexibility to control several inverter-based resources or distributed energy resources on the field. So, so that's basically on the management side. If you go a step back and look at the type of devices that support devices that goes with the DERs, one big asset or controllable asset in the form of energy storage is important. So this is a sketch in which you can see the energy storage required or energy storage implementation on the field, adapted from the conventional grid sketch. So that's basically what we call it as a grid management, considering one controllable asset, one meaning not one, but one type of controllable asset, such as energy storage, and control of inverter-based resources that can support or work with these controllable assets. That's the second part. And the third, an optimal management framework that could interface with the ADMS or DMS infrastructure with these controllable assets. So that's the goal, overall goal, where these controllable assets can be used for grid balancing, both load balancing as well as stability improvements, and reliability and resilience as well. So with that being said, what we have been looking at in PCEL, we call it Power and Energy Intelligent System Laboratory. We have been working on 3 different type of projects in PCEL. One on the fundamental side, mainly supported from National Science Foundation, where we have fundamental improvements on the newer frameworks and the so-called 10-year time frame kind of framework projects which we used to do. And we also have projects on field implementables with the help of local utility support, Duke Energy, and other industries. And recently, we have been collaborating Duke and few other industries and the university partners to implement larger scale projects, and the one which we're going to talk about today, supported by Department of Energy. So that's one, 2 type of projects, and we also have field implementable architectures going onto the field, supported by industries as well as the local North Carolina Innovation Center. So with this, we have been working on this for last this type of projects for last 20-25 years. I have repository of dissemination activities worked with the local partners from PCEL, and also the center which we have here, Energy Production Infrastructure Center, and associated centers along with the EPIC, which we call it Center for Advanced Power and Energy Research, CAPER. So with this background, I will now talk briefly, next 20 minutes or so, on one grid management architecture that we have developed recently with the help of the Department of Energy funding from Solar Energy Technology Office, namely optimal reconfiguration and resilient control framework for real-time photovoltaic dispatch to manage critical infrastructure. The short name for the project or the tool that we have developed is called REDIS-PV, resilient and reconfigurable and dispatchable photovoltaic infrastructure or management infrastructure. The REDIS-PV architecture, what we have done is we have developed the entire tool with the help of several university partners, national labs, and other industry partners, and implemented the tool in the lab scale, utilizing the DMS DERMS infrastructure that we have at Duke Energy. And then after that, we showcased the tool on hardware in the loop platform, on hardware in the loop scale models, and then implemented or utilized the tool to work with Duke Energy models, and in collaboration with Duke Energy, now currently working on connecting that tool with the DMS and ADMS. So that's basically the architecture. So in this slide, you will see on the left-hand side what conventionally DMS is focused on. On the right-hand side, you will see the DERMS infrastructure architecture there. And then on the bottom right, you will see the REDIS-PV architecture. So the architecture includes management right from the control aspect of the distributed energy resources, including one type of controllable asset called energy storage. method of control, grouping of those DERs fictitiously, we call it clustering, and the method of control is called cluster control. These are the two main aspects that UNC Charlotte was looking at in collaboration with other universities partners. And then we have the area control that goes along with that. Then this architecture, we have also extended that to other functionalities, include protection, reconfiguration, optimal power flow, which are contributed by other partners in this project. So today we're going to talk about the main control of IBR and management part of that. So which includes cluster control, area control, micro system management, as well as control of the inverters in not grid connected mode or in the microgrid control framework. So this sketch is an overall integration framework for the so-called Redis PV tool. This is a little bit busy sketch, but I'll try to explain it, at a high level. So in this tool, we have a few, we call it modules in the tool. And in this tool, we have protection reconfiguration, which happens in, all time scale separation or time frame, which we have included in this tool. So the smallest one is protection reconfiguration framework. Then we have the power flow based information exchange, as that's what used in the utility, as opposed to state estimation. We have that happening at the next time scale, which is like in 1 minute. Then we have formation of those cluster, have cluster control. Cluster control is faster in 5-second, 10-second based control. And area control, which is connected to 2 level of optimal power flow framework, all implemented in the industrial grade tools, including OpenDSS, SIME, interface through Python script, collecting data from the software, and that same data structure, which we call it the JSON data structure, you can utilize to collect the data from the field. So this architecture, we tested that utilizing the models first. And the architecture also has a communication framework that can be looked like a field communication from the head end, for example, wherever the Redis PV sits, closer to a SCADA-enabled substation, suppose it sits from there, looking at the cluster or a group of DERs through the communication stream. So we have utilized the field communication, implemented that in an open framework utilizing NS3 with the help of our partner at the New Mexico State University. We have implemented that in 2 data streams, implemented in 2 different places, one in New Mexico State University, another UNC Charlotte, and exchanged the data through the NS3 platform. The same architect, NS3 platform, just not on the communication framework, we also utilized it for assessing the cyber-related aspect, including the packet drop, delays, latency, and the effect of that on this architecture. So it's a part of the project. So this Redis PV tool that we first tested it in a software platform, and then we have utilized the same tool to test it in lab hardware, utilizing the grid simulators and the hardware in the loop test through real-time simulator, and then tested it in the field using a Duke model and currently implementing that with the Duke DMS terms. The tool also has a visualization capability where you can, or operators can see the groups of DERs and their functions and how the power exchange happens. So that's another factor for the tool. Now, the tool at the end, during the project, towards the end of the project, we have used the tool for for use cases that we have developed to test it in a few different use cases. We have 4 use cases that we mainly used to evaluate the tool in different time scale, which includes the improve the dispatchability of those photovoltaics along with the battery energy storage, ability to support grid level set points given either by the DERMS or DMS from the grid, or auxiliary service support, improving the resiliency during the outage conditions that happens in the field, and then implementing the communication framework that helps evaluate the tool's performance during any cyber-related events. So that's basically the tool. So now I'm going to talk briefly on a few of those aspects on the tool. So the first main part that the tool is capable of is to develop virtual clusters on the distribution network where you have DERs, and each of those clusters together or separately can be controlled using a controllable asset, for example, battery energy storage. So the cluster development is based on active power flow between cluster, and we call this connection between cluster as ties. And the main goal is to make sure that the clusters are formed where the tie flow is very minimal. So the reason for that is to make sure these clusters are independently formed, so that there is a load generation balance happening all the time. So if required, if there are active devices there on those connecting points, for example, switches, you can utilize this framework in between to isolate it if you want to intentionally isolate between groups of those clusters. And on the flip side, if it happens based on a protection logic, then you can actually move these clusters based on the physical device which happens on the field. So that was a thought process there. The cluster can also be formed using looking at the reactive power sensitivity or reactive power balance on each of those areas, which I think is important with IBR-based resources, considering the fact that the inverter's reactive power based on the capacity can be utilized at different time scale, at a faster time scale than the legacy controllers. So the cluster formation, identification, and automation is the key part. This is some mathematical framework for the cluster. So when we looked at the cluster, one thing which came out, stood out for that matter, and fundamentally is what we call it as spectral clustering based approaches. So there are 2 main approaches there. One is based on k-means, another on k-penoids. When we looked at it, we found that 2 things stand out. One, the cluster creates, the spectral-based clustering approach creates a discontinuity. Sometimes it is non-optimal and or suboptimal. What they mean by that is the cluster will be only too many clusters, and sometimes clusters are not formed in connection with the physical area. It's in different places. And at the same time, the clusters are discontinuous. So you see some of the results in here, where you can see the power flowing between clusters are higher as opposed to be lower. And the cluster colors, which you can see that happens in different places in the same color, which means that clusters are not contiguous, it's discontinuous with respect to the space. So we came up with the 2-layer spectral clustering approach, which includes the development of eigen vectors and eigen gaps, which happens on the analytically happens in the system when you have system data information available, and then utilizing that to create the Laplacian form for the system. And we have tested it in several places and realized that the cluster continuity of the clusters are maintained. At the same time, the clusters are optimal in nature. So after we did that, then we developed what we call it as a cluster control. So objective of this cluster control is to make sure that each of those cluster load generation balance happens, including the reactive power capability of each of those clusters. That's the main goal. So for the cluster control, you should have a controllable asset there. And we used battery energy storage as a controllable asset. You don't need to have battery energy storage for every cluster, even though we have, for example, 30,000 node power distribution system can be used as an example. And if you're looking at a three-phase controllable asset on the three-phase scale, suppose you have the 600, 700 nodes, which are three-phase in those, you can have 10 to 12 controllable asset in that whole framework. And if you have 2 or 3 for that matter, that's also okay. We can actually group the clusters with one controllable asset in one cluster form. So that was a thought here, so that it can be field implemented and also can be scaled up in future. And most importantly, can give you the size and location of those controllable assets which has to be implemented on the field. So the one of the control framework that we originated from for this architecture was using predictive horizon approach, or model predictive control approach. So you can see in here there is a objective function where you are looking at the error reduction for each of those area. So you can use that for what we call it as smoothing, meaning the power in each of those cluster at the entry point should be straight line when you look at it visibly, even though you have variability on the each of those area for the distributed, because of the distributed energy resource. You could also use a area set point for this tracking error. So that's basically the architecture. So this architecture, we used to look into the local objectives for cluster, which is power balance, and a global objective from the feeder head, where you can give the set point. It could be a set point from the substation, or it could be a set point for, like I said before, auxiliary services set point, including the management of the controllable asset, for example, the state of charge and the tie line minimization. So here are some mathematical framework in there. So we tested this on IEEE, 8,500 node system, extracting 650 bus from there, which is the three-phase node on the three-phase side, and utilizing this architecture, testing it with few PV farms and battery energy storage, and then seeing whether the PV BESS combination can be used to develop the cluster and also controlling the cluster. So here is an example at a different time of the day where the clusters are formed. This is in the morning and then later in the afternoon. We used the real-life PV profile on the system, which has a spatial profile difference from different points. So that's also utilized as a data set from the field, and then mapped that. And the size of the PV farm and the BESS is selected random. We're not specifically optimizing either the size, location, or the number. So in any case, you should be getting the cluster. That was a whole thought process there. So if you can see the cluster forms are different depending on the different type of the day. So to verify that, we will be looking at to see in each of those clusters whether we have some load generation balance. So you can see that in each cluster, the set point that is coming from the feeder head is acknowledged based on the cluster. So this is without control comparison, with the control static cluster. And another type of clustering form that we have, which has been implemented in the field, is what we call its dynamic cluster. The reason for having two of those type is to look into, if you are more worried about complexity, not concerned about the error much, then you could go either way. So we have flexibility there. And that area reference tracking, whether it happens in the feeder head, that was a whole idea. So that area reference tracking happens, and at the same time, each of those clusters are pretty much tracking its own reference points on the whole group. With the respect to the reactive power, we also checked the overall voltage profile and the voltage profile balance with DER variability. So you will see that the voltage to profile balance on each of those nodes that we have tested in, for example, in several nodes, on weak side as well as on the stronger side, will have better balance with respect to the voltage profile as whole. So that's one use case. So the second use case, we used it to also look at to see whether it can improve the resilience and energy equity. So in the resilience space, we use the cluster formation for critical load support and at the same time, load management and DER control. Now that we attributes of those cluster formation is that is situational awareness based, which means that based on the grid situation, these clusters and load management can happen. So here is an example in which we defined the load. So when we work with the utility and talk to them, there is nothing called the critical load or critical infrastructure, even though they would like to supply the power to hospitals and schools and other infrastructure as the primary one. But the overall goal of the utility obviously is to improve the reliability of for all the loads that are connected to the utility. So with that in mind, but we still divided those load segments into each of those parts from the higher critical level to the lower critical level, and then defined the three main baseline form of the resilience. One, the loss of load. Second, the economics associated with that, and then so the third one is the time, the social discomfort that we qualified in the form of or quantified in the form of time. So how long the power is out for that matter. So it's as a discomfort to the user. So here you will see 2-3 different type of parts on your objective function, which includes the outage time, efficient use of PV generation, reducing the economic loss and social discomfort. With this combination, we have looked into what type of support can be useful. And if the support time changes, for example, hour on the top, you can see 8 hour support versus 1 hour support, how you can manage the variability change with respect to the, for example, the state of charge of the controllable asset or the duration in which the controllable asset has enough capacity to support this variability on DER. So this is an important frame that you can see, your operator can see, and then look into where you need to adjust with respect to the management of those controllable assets. So in this slide, just trying to showcase the situational awareness piece for the cluster information. You can see that the cluster that's formed during a partial outage, how those clusters are formed, and the situation changes to, for example, in a reconfiguration. Not going into the reconfiguration framework and the protection framework, which is implemented with the help of our partners in this project. So if you have a fault on one area, and then how that fault became make the system islanded, and then how the cluster still maintains the remaining part, and then try to see if we have load generation balance can happen on those. So you have see the cluster number here, as you can see on the reconfiguration part A, B, and then bringing that part of the system which is live can be grouped together on part C. So if you move that into, like I said before, in the form of switch-based clustering, you could include wherever the switch positions are. And again, one of the feedback from the utility is not to have a mandate the number and location of the switches, because that can come based on the asset management methods on different utility. If you have a switch position already there, whether you can try to make clusters along with that. So we were able to see that as well. The use case 3 is implementation on the field and then field validation. So this is a field data information from one of the feeders in the Duke Energy territory, where we have 3,900 or 3,100 node. and 2,000 boxes. We have few PV farms, or 2 or 3 PV farms they are actually currently working on the larger scale, and around 50 odd small scale PV generation. So we said that, well, small scale PV generation scale, we will use those devices, but we will not, we will only make groups and clusters on the small scale and the large scale together. So we have combined them together, and then the system do not have a battery energy storage. So we have actually included the controllable asset as battery co-located with those large-scale PV farm. So here is a network information with the number of reclosers, and this is fed from 2 different points on 2 different locations. So there is also a flexibility to power from 2 different sources. So it's a large PV and the small PV location. And one of the use cases Duke wants to have is to support some kind of frequency signal coming from the transmission side of the house, and then see whether you can honor those signal, so in the form of an ACE. And that is a signal that is given to us. We mapped along with the variable PV or variable DER in the system, and then looked at that as a reference signal. So the goal is to actually see if you can track the ACE signal and also make sure that you balance the output from the PV farm. So here is one of those power balance that happens on the grid. Pretty much except for this specific area, you were able to balance it properly. And this is because at that time you have both the photovoltaics and as well as the A signal coming, and we don't have enough capacity, which is also good in the sense you can see whether we need to invest in there or not. So asset utilization investment can be monitored at that. Like I said, this tool also were able to do some kind of visualization. This visualization piece is not obviously a professional grade. We still have to expand that if you wanted to. If you want to use in the field. So currently utility is working on that aspect, but you can see the voltage profile, clustering of those clustering information on the field. And then you can see the voltage profile changes happens during the grid event when there is an outage, a normal operation, and the reconfiguration part. You can also see the metrics associated with that. If you were to look into the metrics, for example, resilience quantification, information of that. And then we have a few other aspects on the projects that we utilized to improve the overall cyber security related aspects. So you can see that in the overall visualization. And few other things about the project. You can use this link to look at some of our webinars that we presented to the IEEE group. So that's basically about the tool. I'm just going to talk next 10 minutes about few other important aspects that is required to be implemented. One is on IBR control. So as you all know, or maybe some of you are working also in this area, the control of DERs considering grid reliability and resilience is important, especially with respect to the grid codes and the connection of those IBR controller. And this is one requirement developed based on the NERC guidelines for the current injection or current support requirement from the IBRs. And basically during the unbalanced conditions and fault conditions where we have injection from the IBRs, negative sequence current operations. So there are a few other, for example, there is a UK grid code. There are a few other grid codes which happens all over the world, which includes the magnitude, angle, timing, reaction time, rise time, overshoot, all are control related aspects. But it's important to have this included on the inverter-based resources. On top of that, we should also include features that extend to primary level controllers, where including this right-through capability for those DERs, secondary level controllers, where we need to have voltage frequency synchronization, and network level microgrid management in the form of tertiary level controller. So there are several framework that happens, and also there are black box models coming from the vendor, information-based controllers that coming in operation in different framework. So one solution that is currently being tested in the field, hopefully will be implemented in one of those inverter OEMs, is a unified control architecture that can actually not just has a capability to write through or look at the make sure the grid core requirements have been met, but can also inject the required sequence current or the combination of those sequence current during the time of outage. So what we have done is we have looked into a real IEEE system to test this control architecture. And then test it on a real-time simulator hardware. Now we are currently in the process of testing it in the field. So here is an example of a modified distribution network with those islands on IEEE 123 bus system. And the control architecture has unified the controller, which means it can work on the grid connected mode and on the islanded mode without having to move from one control architecture to other. Can also work on different objectives on different levels. So we have, you can see there are two types that's mentioned here, type 0 and type 1, which includes the grid connected and islanded mode condition. When you and then two sequence components representation on the architecture, which is positive sequence for power tracking and frequency voltage nominal values, and the negative sequence currents to mitigate power ripples and steady the or balance the voltage during steady state condition. So I'm just briefly going through this architecture. There is, you can see some references, you can look at that. The architecture, the backbone includes power tracking on the grid connected mode, power tracking during islanded mode, power ripple mitigation on the grid connected mode, and balancing voltage on the islanded mode. So here is an example of those, a few of those results from this architecture. You can see on the top right, the proposed controller on the grid connected mode have current proportional to the voltage, and that current that has been supplied has a negative sequence component as required, as opposed to what's there in the literature, and also can mitigate the harmonic content. On the flip side, on the islanded mode conditions, this can honor the grid core requirements and always can supply a negative sequence to balance the voltage, both in farming and following conditions, and as well as the capability to ride through based on the one of the critical factor for the inverter-based resources is the supply of the current will be very close to the maximum supply of the current during fault conditions will be very close to the nominal load current. So with that, whether you can still be able to contribute towards a sequence component injection is basically some of the things that we were testing out. One other field implemented architecture, which is also being patented and then utilized by the utility, is operation of the battery energy storage for multiple functionality. We call this as stacked control approach. So I just wanted to show you a picture of it, and the controller is field implemented and tested and then utilized by the utility in collaboration with the local utility, Duke Energy here, where the energy storage functions, including capacity firming, energy timesheet, voltage support, all can be included in one architecture framework. So the co-located battery energy storage, grid scale connected with a PV farm, co-located to a PV farm, can be utilized for support of the photovoltaics and at the same time support of the feeder associated with that photovoltaic where it is located. So we tested this architecture in, it's a little bit almost 10-year-old now. So tested this architecture in 2013-14 timeframe, field implemented with Duke, and then in 16-17 timeframe, they got it adopted onto the field currently being utilized in the field. The reason for me specifying or talking about this is to show you the newer architecture that we are building in can be connected to the existing architectures infrastructure that has been developed before. That is basically talking about that pathway on how those work can be field implemented. So with this, I wanted to summarize like few takeaways. I think it's important to look into area-wise requirement for an electric grid. This happens in the bulk grid and at the same time on the distribution network also, to see how you can virtually or physically connect, develop connectivity between intra and inter areas on a network, a larger network or smaller network, which can help improve the reliability, resilience, and equity. So that type of management has, I think, in my opinion, longevity and future credibility. And if you want to have that implemented, especially on the distribution network, you need to have only fewer level of controllable asset support type that can be implemented. Otherwise, it will become complex. So improving technology adoption and management of grid support system, utilizing, for example, battery energy storage or one or two type of controllable asset is much more meaningful, even though you will be able to scale it up and manage several distributed energy resources. Provide value-based management approach, which means that it can be implemented. It has got a value quantification, not necessarily in the firm in terms of cost, but it has got a value quantification, which is extremely important. And we have shown that in our some of the work in the past, how that can be achieved. And that's one of the directions that we'll be taking up in future as well. So here is a few select publications pattern list in here. I have mentioned some on the slides as well. And I would like to acknowledge the PSEL researchers and alumni and the Redis PV team. There are several other members. You can look at the website. We have a website called redispv.org, where you will see the complete list of partners on the project and as well as the project details and deliverables. With that, I will see where I can stop my presentation and will answer questions.
Thank you very much, Kumar. That was very interesting talk. We really appreciate that. So let's go to the Q&A by maybe first start people online. So if you have questions, please unmute yourself and ask your question.
Oh, now finally I can see the room. I saw the room with only you sitting there. Now I think like a good group of members there. So it's interesting to see. I think there is Charles.
Yeah. Yes, Charles, please go ahead.
Fantastic presentation, Shikumar.
Thank you.
What is your thought on how a very tight microgrid control system will fit into your clusters, as opposed to sending direct controls commands to the controllable assets within the cluster? Would it make sense to send control commands to a microgrid within the cluster?
Yeah, I mean, you could send controllable commands to a microgrid within the cluster. Essentially, we think that the cluster can be formed as a microgrid. So if you have control functions of that microgrid that happens on one of the asset in the microgrid, and if you wanted to manage that asset, obviously we can do that. And we think that's will be a part of the cluster anyways. But what we want to do is not just control the asset in the microgrid. We wanted to also make sure that those, let's assume that that cluster defines that microgrid and cluster made sure that's a microgrid and we can send the signal. We also wanted to make sure that that cluster or that microgrid can connect or we can send controllable signals to other microgrids, so it can form in a network and in operation. So definitely, yes, you could utilize. Now, if you come from the other angle, let's assume that you already have defined a microgrid and you have an asset there, and you said that's the main asset that controls a microgrid. We can still implement the cluster farm. That cluster will be having probably that microgrid or the large scale, rather 2 or 3 microgrids for that matter, still can utilize that. So it works in synergy. Even though the purpose is slightly different, you can utilize that asset in a microgrid, if that makes sense, Charles.
Yeah, I was thinking that would make it simpler because you have fewer commands for the cluster to send. This cluster will only send commands to the controllable POIs of the microgrids, and that will then let the microgrid be responsible for the DER and the battery control. And then the cluster is responsible for setting the POI set points. And that way you get an additional layer of control. And it also makes it so that the microgrid controller is sort of an encapsulated object that the cluster then controls. And that'll make it easier. That'll make it easier for the industry to accept this technology, because right now, as you point out, the utility industry is really wrestling with what is the best strategy for control. And many utility companies are thinking of a horizontal control approach where, hey, the master DERMS is going to control all the DERs behind the meters. And that is not going to scale well. But if we scale it in terms of clustering, and then the clusters own microgrids, and then the microgrids do the dirty work of 60 hertz control or 10 hertz control to regulate their POI subject to the boss, which is the cluster. And then there's a boss on the cluster as well. So it's a multi-layer hierarchy of controls that are much simpler than a horizontally distributed control system. People are talking about, I have a 3 million bus problem I have to solve. So how are we going to control the Detroit area with the 3 million bus problem? And so I think the strategy of clustering and then going one step deeper into a microgrid below the cluster makes perfect sense. And I really like your idea of dynamic clustering. That's something that is really, from a control theory point of view, that's sort of a logical way to control the grid. But then the added thing that you point out is the fact that the clustering can be dynamic, which I think is also very important, especially as we see the flow variations during the day. We know that the optimal control structure should change during the day. So I really like your approach, and I hope we can move some of this technology forward.
Yeah, and that's what we are trying. I don't know how much you work with the utility space, and it's still there a lot of stigma, right, with respect to adaptation and then using in the field and so forth. But the approach we are taking is exactly like what you said. We will be looking at one point in that cluster or a group as a kind of point of contact or the main asset that we can send the signal to, and then the rest of those assets can be managed in that group. So that's actually working very well. In the sense of approaching to the utility and talking to them. So we are at the point that now the utility is kind of accepting that framework, but slowly trying to penetrate to the utility space. It'll take a little bit of time.
Well, another 50 years maybe. It's very
exactly.
And it's frustrating because we need to have this concept in order to get high penetration of renewables. If we want to go to 100% renewable, I see no other way than using a hierarchical structure.
Exactly, exactly. And that's one of the challenges, especially in our country. I don't know, people talk about 100% renewable already achieved in some other part of the world. When I travel and then talk, that's a different, scenario altogether. You cannot implement. It's not like, like what I'm saying is that's not a one-stop shop kind of thing, right? You cannot implement that in our place. So at least for us, this is important. But it's a slow-moving process, obviously.
Yeah, we'll get there. Well, thank you
Absolutely.
very much for your talk. It's
Thank you.
It's I think this is very much in the right direction, and compared to other studies we've seen, it makes a lot of sense, and from a control point of view, it makes sense. And the big issue we have is convincing the utilities to adopt the approach.
Yep.
Thank you.
Hopefully we'll get there. Thanks for the comments.
Yes, Kumar, for your information, Charles is the CEO of the company. They work at the microgrid type of control. What is the name of the company, Charles? It's Pixel?
Oh, it's called PICE, like
PICE. Yeah.
Yeah, we're a small company in California, but we
how do you spell Charles?
PXISE. So we're an 8-year-old company, and we've done about 20 microgrids, but all of them have been challenging because of discontinuities between manufacturers' equipment, incompatibilities between the battery manufacturer and the inverter manufacturer, and et cetera, et cetera. So it's really been a hassle, and we've been trying to encourage the industry to adopt a standard modular microgrid, so everything will work together. The battery, the inverter, and the controller all should work together. And rather than spending several years on every microgrid, I know Duke has done that also in some of their microgrids. It's taken multiple years to get their microgrids installed, and then the microgrids didn't perform as they expected, and so forth. So we've had the same type of experience, and it's very clear to me that not only do you need a modular piece of hardware that is the microgrid guts, but then you need this hierarchical structure on top so that the whole system can be automated smoothly. So that's another huge issue. And of course, we all are trying to address the problem of how do you convince the industry to use grid forming inverters in your microgrids, because everyone today is using a very expensive inverter that can operate either in grid forming if you're in island mode, or grid following if you're in connected mode, and there's no reason to do that.
Right.
And the industry doesn't believe that yet. So it's
that's exactly another point that we are talking when we talked to Duke, and we wanted to showcase this. Even though we wanted to show that as like a unified control architecture, the central idea of that control framework is also to show to them that you don't have to differentiate between farming and following in different modes of operation. You can have an architecture that can, change, or you don't have to even say what is farming or following. It should work everywhere. That's all it is. These are kind of a terminology that we create for ease of study, but can also be firing back on us, right, with respect to the terminology. So just wanted to showcase that, because to the industry. So I exactly understand what you're talking about with respect to the challenges, and with respect to adaptation and challenges working with the utility.
Well, you're definitely on the right course. I mean, we're 100% with you on your approach. We believe it is the right solution to really get to the 100%. Now, it's going to take a long time to get to 100%, but there are going to be Pacific islands in particular that are driven to get to 100% because of the cost of fossil fuel. They want to go 100% as soon as possible. And we need to show in these Pacific island or any island that, hey, you can get entirely off of fossil fuel by battery storage and PV and wind, putting them together in a structure like you have proposed, that makes it easy to maintain and easy to service. It's robust, it's resilient, etc. And so we need to get something working in sort of a big island and show the industry the benefit of going zero fossil fuel. But we can get there with this architecture.
Thank you.
So I'm very glad that you're taking this approach, because some are not, you know.
Yeah, thank you, Charles, for your great comment, questions, everything. Okay, any other question? No, online. Yeah. Okay, you guys.
Yeah,
You guys are all guru of the distribution system. Yeah, just
yeah.
ask questions. Yeah, you work on distribution system too?
Most of my lab does.
Oh,
yeah.
Oh, you too?
Yeah,
Oh,
including me.
Go ahead. Go.
Thank you for the great presentation, Dr. Kamalasadan. So I just wanted to ask some questions to make sure I understand what you are doing. So to begin with, you do clustering in kind of almost real time, like in the order of minutes, right? In your dynamic clustering case, I guess.
Yes, yes.
So what rules does a cluster follow essentially? Like, why are you clustering them?
So the fundamental need for clustering and what we want to achieve with clustering is a load generation balance when there are DERs in different points on the electric distribution system, and where we can get the right load generation balance, or best or optimal, we call it, whatever it is, the term is load generation balance that happen. The reason for doing that load generation balance, if you can identify that, what we are thinking, we can make sure the controllable asset in that region can be better utilized rather than centrally managed or centrally sent signal from a head-end substation or some. So that's the basic practical need or practical thought behind this clustering, if that makes sense to you.
Yeah, that makes sense. However, since you are optimizing in kind of real time, my question is, it seems that first of all, what are your controllable assets? Like you have DERs which have inverters, so you have like 4-quadrant control over the reactive powers. Are you also controlling their real power? Like, are you curtailing them or doing anything to the PV values?
So the controllable asset is all the time active power controllable asset. So you also talked about reactive power. So let's decouple, meaning decouple not in the sense of Newton-Raphson power flow, but just not talk about the reactive power now. So from active power, when you are talking about active power, the controllable asset is only batteries. Because if you go with the utility and say that I have a great optimization algorithm, which has a minimal curtailment, but still curtail the photovoltaics, we cannot reach 100% renewable target and everything, because you are curtailing, you are actually getting rid of it, right? So what our thought was to have the controllable asset only batteries. Now you may ask the question, well, if that's the case, do you have to buy several batteries? The answer is no. You can actually have 2 or 3 main grid scale battery that can be implemented in the utility scale, and then can use that as a controllable asset. That's from the active power side. On the reactive power side, you may also mention about reactive power. Obviously, we do clustering on the reactive power as well. On the reactive power side, as you know, the inverters are giving you free reactive power in general, as you may talk it in that sense. And except for the capacity related boundary you have to honor. For example, if you have 1.5 MVA inverter, you can do some PV from 1 MVA. This next 0.5 square root of whatever that is a reactive power that you can get from the inverter. But you can at least get reactive power support from the inverter. Still, we will utilize large scale photovoltaics, inverters connected to large scale photovoltaics. For example, in the Duke territory, we have few inverters which are oversized, basically for the reactive power sense, for the PV farms. So you are utilizing only those, still not the battery inverters are there. On top of that, 2 or 3 large PV inverters for the reactive power. These are our controllable assets.
Yeah, thank you for explaining. But as far as you said, you are using batteries to control your active power balance. So, like one question I have is, how are you getting like the original set points of the SOCs? Like it seems you are using an SOC set point and then minimizing its deviation for any time step, right?
No. So state of charge is not a grid level requirement or not a set point requirement. It is actually a requirement for the device so that we can actually increase the lifetime of the device or longevity of the device usage, right? That's basically the state of charge. State of charge is the state of charge balance is a constraint, is something that's coming out of the device to make sure the device can be operated. The set points what we are giving to the battery energy storage is either the minimizing the variations for the photovoltaics, we call it smoothing on each of those cluster, or the grid level initiatives that is given from DMS. For example, the power that is coming required to be maintained constant at the feeder head, or in between the capacity of the feeder head transformer, or the set point that is required on the transmission system, for example, the grid ancillary support. That is basically the set point, not the battery, state of charge. Now, our goal is with that set point for a duration of time, for example, 20-minute time scale, like if you look at the average movement of time with respect to time, 20 minutes time scale or 30-minute time scale, can we make sure that battery has enough juice, which is basically coming for the state of charge, your thought process there. Can we have battery has enough juice to supply to make sure that objectives have been met? It could be a smoothing of the PV, or it could be the grid level objective. Can you have enough juice so that you can utilize that same battery towards the, during the 24-hour lifespan, right? Of course, in the 24 hours, when you talk about some of the batteries will not be able to utilize in the nighttime, or for example, and then you don't have that volatility or variability or intermittency on the nighttime anyway. So having said that, the set points are not coming from or designed based on the state of charge of the battery. State of charge of the battery is included in there to make sure that the battery can be utilized throughout the time scale in the formulation.
Yeah, thank you so much for clarifying. Yeah, I got it. Thank you so much. Yeah.
Okay, so to respect Dr. Sukumar time, because we already over 1 hour, so maybe just last question. So if you have, who is the lucky person?
Okay, I have a question.
You are the lucky one?
Okay, so I actually work with the nearby utility company, and we're doing similar kinds of things, but we're doing it from more of like a economic control signal kind of way. So we're working with PNNL. We do this transactive energy kind of thing where, different types of DER assets can anonymously be able to send some kind of range of values in which it's able to operate, and then it will do some kind of centralized control. I guess you say from like a cluster perspective, it would be a centralized control with these kinds of available ranges that are submitted on, say, like a 5 or 10 minute period of basis. And I kind of wanted to hear your perspective on, getting more of these controllable devices, because it sounds like here that you have basically 1, 2, 3 main controllable batteries, but it would be a lot more beneficial if even more assets could kind of communicate with each other. So what do you think some of the challenges are of getting, customers as opposed to utility owners to try to participate in this kinds of communication? We're trying to do it from like an economic standpoint, say, okay, we'll give some kind of price signal to control them, but like, what do you think?
So first of all, just a clarification. I think you're talking about the behind the meter kind of devices, right? Where you can participate on the grid. Yeah. So throughout my life for last 25 years, and I have collaborated also with the PNNL and some other folks there, I have been hearing about transactive energy systems, and probably that's saying with Dr. Saeed and almost everybody in this. So we have been trying to implement that technology from economic standpoint, like you just lightly mentioned, with the load set point or the demand response, what we call it, which originated in 1990s and things like that. So that framework is actually very meaningful to me. However, the bad news about that framework is the convincing to the utility. I mean, all these frameworks, it's difficult to convince utility for that matter. But the bad news about that framework is actually how can you include multiple devices and how can you control multiple devices even though you are not the controller? So that's one of the challenge. So why I'm saying that is, let's assume that you're giving a signal to somebody who is your homeowner. I mean, who is a homeowner for that matter, and utility is asking them to manage or control their device, but you don't control, the homeowner controls, and you don't have a visibility or controllability to say they control properly or not. Suppose you may say them to control and they may not control. Who is having the liability? Again, the utility. Because they may not control, then you are still going to find out the best economic point next time and asking them to control. So it's kind of a pleading, and it may not happen. So two things are there in control. One is basically utility side when you talk to utility. One is the number of controllable points. It scares the utility. You don't know what to construct and where to end. The second part is if it is not directly under utility jurisdiction, they don't know, they cannot, or rather it's not possible for other folks to control. So that's basically two main field implementation challenge to me personally. If you ask, even there are a lot of colleagues and friends I have in PNNL and several other places with respect to transactive energy, these are the two main challenges associated with the transactive energy. Now, if you ask the question, well, can we try to include these controllable assets or make more number of controllable assets? It can only be possible if, for example, if you talk to the utility, if they have a direct ability to control. Otherwise, they will deny it. No matter whether you are now or 20 years from now or 30 years from now, if they run the business, that's what they have to do. So if you have flexibility to do that, either by having a front-end device that is controlled by the utility to manage the back-end device, that's what we are trying to do with these kind of approaches there. You cannot implement. So my thought there or answer there, there is a lot of value in what we are trying to do with respect to transactive energy, and I can see the value addition there. However, to implement that, we should have an approach or a pathway to reach there, and that needs to be really thought through. And we have not been doing that intelligently so far, I call it, for the last few years with that technology, basically. If that makes sense. That's my personal opinion about transactive energy.
Thank you.
Yeah, thank you very much. Yeah, thank you very much. That was really very engaging talk. We really appreciate that, and really appreciate you even went way above your allocated time. We appreciate that.
No worries. Thanks for inviting me, and with friends and colleagues like you, it's also important that I should honor, not just because I should honor, also because I can socialize with you all and then see. So it's great to see you. Hopefully we'll see you very soon in near future.
Yeah. Hopefully see you sometime soon. So yeah, thank you. Have a great day. And goodbye.
Bye.
Yeah, thank you. Okay, thank you guys.